Welcome to our IRI seminar series. I have the great pleasure of introducing our distinguished speaker, Kyunghyun Cho. Kyunghyun is an associate professor of computer science and data science at New York University and Cypher Fellow of Learning in Machines and Brains. He is also a senior director of frontier research at Genentech, and he was a research scientist at Facebook AI Research. Kyunghyun received his PhD degree from Aalto University, and he was a postdoctoral fellow at University of Montreal. Kyunghyun tries to find a balance among machine learning, natural language processing, and life, but almost always fails to do so, as he told us. Today, he will talk about techniques for learned data augmentation in natural language processing. Since the knowledge of invariances and equivariances is limited in NLP, such data augmentation procedures are a challenging problem. I'm also excited that we will learn how such a learned data augmentation can be used to predict generalization. Looking very much forward to the next hour. Over to you, Kyunghyun.
Well, thanks for the generous introduction and also the invite. It's unfortunate that it has to be remote, and somehow during my, let's say, 5.5 years in Finland, I've never managed to visit Austria. So next time I'll make sure that I be there in person and tell you about other stuff that I work on as well, in particular at Genentech. But today, let's focus on what I've been working on during the past, let's say, 2-3 years at NYU, in particular with focus on data augmentation for natural language processing. So before I start, I want us to keep in our mind of what we call manifold assumption, which is the intuition as well as the science behind the success of data augmentation in recent years. According to the manifold assumption, the high dimensional data lie roughly on a low dimensional manifold. Now, let's not get stuck in the precise definition of what kind of manifold we're talking about. But what we need to keep in our mind is that all the kinds of data, different types of the data that we have worked with in machine learning, almost always lie in a much smaller, let's say, portion of the entire space. And then there is a reason why our machine learning algorithms can actually successfully learn any complicated function on the problems that we want to solve. And then what is this small, let's say, portion of the entire space? That small portion of the space is where the realistic looking data lies. So what that means is that if we start from some realistic looking data, there's only a small number of changes that we can make in order to ensure that the examples continues to look realistic. And then that degree of freedom is so much lower than the actual, let's say, dimensionality of the space. There's an extensive discussion about this manifold assumption and its implication in machine learning, in particular for deep learning, by Yoshua Bengio from his technical report in 2009. I highly recommend you to take a look at it. But anyway, let's keep this in our mind as I try to explain what we have been doing in terms of data augmentation by relying on this manifold assumption. Now, going all the way back to the very basic, what we do almost always in modern machine learning or the modern deep learning is what we call expected risk minimization, so what we want to do, not what we do. What we want to do is expected risk minimization. And what it does is that we are going to look at all possible data points in this entire space. And we're going to talk, because I'm going to talk about supervised learning, I'm going to always put X and Y together. So we're going to consider all possible combinations of X and Y. And then for each combination, I'm going to look at how well my model F works on the particular example, which is measured by the per example loss function L. Now, of course, we don't want to care about all possible combinations equally. Instead, we want to look at the combinations of X and Y that are more likely under our data distribution P data. So what we do is we're going to compute the weighted sum of these loss functions. However, each and every point is going to be weighted differently according to this underlying data distribution P data. Now, unfortunately, we really cannot do this directly or exactly because first, P data is not available. And even if P data was available, it's often, and I would even say that they're almost always intractable to consider all possible input-output pairs. So instead, we do empirical risk minimization, where we only use a small number of data points, so X and Y combinations, drawn according to this P data, the underlying data distribution. Then we're going to only look at the small number of examples and then on those examples, how well our model works. And this makes it suddenly tractable because we don't have to take into account all possible combinations of the x and y. And also, we don't really need access to p data. All we need is this training set D that is supposed to consist of all the data points that were drawn from this p data distribution. Slightly different way to write this is to consider all possible combinations of x and y as usual, as we wanted to do with the expected risk minimization. However, we say that we replace the p data, the data distribution, with this mixture of the Dirac delta distribution that only puts a non-zero probability on the points that we observe, that is, on the points that are part of this training data set. So what you can imagine is that we want to in fact look at the entire space weighted by this p data, and then of course this p data is not going to be uniform, and then p data is going to be concentrated around this data manifold according to our manifold assumption earlier on. And then most of the training examples are going to be drawn from this data manifold, because this data manifold is so much lower dimensional than the entire space. And then most of the probability density is concentrated on this data manifold. So what we are seeing is that we are going to draw some of the points from this data manifold, and then we try to look at the associated risk or the loss function, and we try to minimize it. And that is going to be the empirical risk minimization. Now, what you see from the previous slide is that that's not really what we really want to do. In fact, what we really want to do is vicinal risk minimization. That is, if we had some idea about the neighborhood structure, then what we want is that for each of the data points x and y that exist in the training data, we're not going to only look at that particular points, but we're going to look at the surrounding or the points that are in the vicinity of this xy pair. And then we are going to look at the weighted average of the loss functions in this vicinity. And then that actually can help us cover better the actual data manifold. Now, of course, there is a big assumption here, right? What is this big assumption? Is that we know the neighborhood structure. And then what does it mean for us to know the neighborhood structure? Is that we know the data manifold. But, it turned out that sometimes we do. Sometimes we don't, but sometimes we do. Let's think about the cases where we know first. And what we are going to do is we are going to separate out this P local, so this density that actually tells us about the neighborhood structure, into two parts. One is the input neighborhood or the input vicinity. So given the associated x, the 1x from the training set, what is the distribution in this vicinity? And then the other one is that given that we have selected one point from this input vicinity, now what should be the distribution over the target or the associated label? Now the first part is what we call as local data manifold. Well, I call it local data manifold. And this can be manually designed based on domain knowledge or automatically learned from abundant unlabeled examples, the latter of which I'm going to talk about much more so later in the talk. And what it does is to capture the local data manifold, and then by collecting all this local data manifold, we can now cover the entire data manifold so much better than just considering these points that are in the training set. And this local data manifold structure essentially tells us about what kind of perturbation we can apply to a given input x, while ensuring so that the perturbed version x prime is going to continue to stay on this data manifold. That is the highly probable region under p data. So that one could be done pretty well based on the domain knowledge. Unfortunately, the second part, that is, what should be the label distribution of this new neighbor or the new example we draw from this vicinity? This one is so much more complicated to design, simply because if we know how to solve this problem or to design this local distribution, we essentially can solve the problem that we want to solve, that is to estimate P of y given x. Because at the end of the day, if we could get this local distribution P of y prime given x prime and y, then we can just build a kernel machine and then use the kernel machine to get the actual distribution over the label of any arbitrary x input. So in other words, we can't really design it. Only thing that we do is we actually impose some kind of smoothness. And then one of the easiest way to impose smoothness is simply saying that the label associated, so y prime, the label associated with the new example x prime that was drawn from the vicinity of x, the input, should be identical to the label y associated with the original input x. And what does that mean? I mean, it just doesn't feel right. However, what happens is that if the vicinity is small enough, narrow enough, then by saying that all the points in this vicinity has to share the same label, we simply impose that our function f that we're going to fit by minimizing this vicinal risk is going to be smoother than usual. As you can see from this slide, what happens is we're going to consider all those points in the vicinities of training examples, and then by imposing that within the vicinity, all the points share the output label together, we say that the target that we build is going to be smoother than usual. And why do we want to impose this kind of smoothness over the data manifold? It's because we expect, and we also believe, in fact, this is one of the most important beliefs in machine learning, that this smoother function is going to generalize better along the data manifold, the space or the subspace of the entire space that we are interested in, represented by the training set D. Now, this is a big belief. Whether this in fact holds or not, we're going to talk about it empirically at the very end of my talk. Now, let's look at some of the cases where we can design this p-local distribution or the vicinal distribution ourselves quite readily. Now, one thing to keep in our mind is that we don't really need to have the explicit or the analytical form of what this local distribution should be. All we need is to be able to draw samples from this local distribution, as we almost always rely on stochastic optimization anyway. And this procedure is often referred to now as data augmentation, because given any data points we have from the training set, we can produce these stochastic perturbations or the samples drawn from this local distribution, and then that has the effect of augmenting the original data with all these perturbed versions. Now, as I said earlier, this p local of y prime given x, x prime, and y is much more challenging. And the usual approach is simply to say that all the points in the input vicinity share the same label. However, we can be a bit smarter. And then there has been a number of work, in particular coming out of the semi-supervised learning literature already from, let's say, 1998, that tells us that we can, in fact, train a model over and over in order to use the model or the classifier that was trained from the previous iteration to provide the labels for these augmented data points or the perturbed data points. And then if we follow the paradigm of code training from Bloom and Mitchell 1998, we would end up with what we nowadays refer to as hard pseudo labeling. And if we follow the Granville and Mangio 2004, where they propose to minimize the entropy, not maximizing entropy, then we end up with what we often refer to as these days soft pseudo labeling. So all these things are possible. I'm not going to go too much detail into it, because all these things are simply our way of imposing different levels of smoothness on the target function. So how do we actually then build this p local of x prime given x? So the input perturbation or the input vicinity distribution. If we know about the target domain that we are building these machine learning algorithms for, then we can, of course, come up with a very domain-specific data augmentation. And then in doing so, what we are doing is to exploit known invariances as well as equivariances in the target domain. This is quite useful for a few domains, such as computer vision, speech, and whatnot, where the humanity has been studying for, let's say, decades, if not centuries. Unfortunately, it's not such a domain-specific data augmentation is often not applicable nor suitable for many other domains, such as natural language. So if we wanted to apply or use data augmentation for a broad set of domains, we really need domain-agnostic data augmentation. But before getting into that, let's first see a few domain-specific methods. In fact, one of the biggest success story of modern deep learning, that is the AlexNet from the Krizhev scale from 2012, relies heavily on domain-specific data augmentation. In fact, according to the paper, random translation as well as the horizontal reflection were crucial in a sense that without these two techniques, they weren't able to avoid a substantial overfitting. They don't even report the validation accuracy without this approach, because without this these two, let's say, domain-specific data augmentation techniques, they really couldn't get the model to generalize at all. So this idea of using some of these random rotations or the random augmentation was pushed all the way by Kubuk, Zoff, Shulen, and Lee in 2019, and they called it RandAug. And what they simply do is to load a image manipulation library on Python, and then trying to just apply a random series of image transformations. And it turned out to work really, really well. It's really nice. I mean, what you're seeing on the slide is exactly the code that they use. And that's the only thing that you need in order to improve the generalization accuracy of an image classifier significantly. Now, although I said that the NLP or the natural language is not the domain where it's easy for us to design a domain-specific data augmentation, that doesn't mean that the people had not tried. Wei and Zhou in 2019 proposed what they refer to as easy data augmentation, which consists of the random series of synonym replacement, random insertion, random swap, and random drop. Now, it kind of makes sense. So if you replace a word with a synonym, then the meaning of the sentence is going to be preserved largely so. And in many cases, the sentence is going to look very much well-formed. Now, the random insertion, random swap, and random drop often do alter the meaning of the sentence, and also to make the also end up making the sentence ill-formed. So, this has been done, but not really satisfying, as it jumps off the manifold. Slightly more satisfying approach is data augmentation by round-trip translation. As the machine translation system has gotten so much better over the past few years, we started to benefit from machine translation, not only for the purpose of the translation, but also for the purpose of paraphrasing. So we're going to start from one sentence. We use machine translation system to translate it into another language. And then we use yet another machine translation system in order to translate it back into the source language. And then unless the sentence is extremely simple and the machine translation systems are perfect, we are almost guaranteed to get a paraphrase, not exactly the sentence that we started with. And then this is one way to introduce a perturbation to the input source sentence that preserves the well-formedness of this sentence, and also to preserve to a certain degree the meaning of this original sentence. This makes perfect sense, and then the advances in MT indeed do give us the ability to create all these paraphrases by using many different pivot or the target languages. However, it's still not satisfying, as it is supervised and also is quite slow. The good MT systems tend to be quite large as well. So already in 2019, I started to talk with my collaborators on whether we can use some of the successes in denoising autoencoders as well as masked language models for the purpose of building a domain-agnostic methods for data augmentation. And one of such effort was published in 2020 at EMNLP. And here we studied the masked language model, BERT, for data augmentation. And this project was led by Nathan Ng, who is a PhD student at MIT and University of Toronto. So what is the simplest possible domain-agnostic data augmentation method you can imagine? We simply add unstructured noise. If we can. So often we cannot really do so. And it does not require any domain knowledge, but it's quite limited. And it's very difficult to ensure that the adding unstructured noise preserves or ensures that the perturbed version of the input is continues to stay on the data manifold. So instead, what we want is to bridge the domain-specific and agnostic augmentation by learning the domain-specific invariances or the equivariances using a denoising autoencoder. So what does that mean? Is that instead of trying to characterize this local manifold structure of the data manifold manually ourselves based on the domain knowledge, and then use that information to build a augmentation algorithm, we are going to use machine learning in order to characterize what this data manifold is, and then use that model that characterizes data manifold in order to perturb examples along the data manifold, so that we get a well-formed, so realistic looking examples regardless of the domain that we are working with. And already from, let's say, already from, let's say, 2006, 7, and so on, we have known that the denoising autoencoder is a really nice and easy way to capture this data manifold. The idea of denoising autoencoder capturing the data manifold is based on the fact that the denoising autoencoder is trained with all possible ways in which we can perturb the input, and the denoising autoencoder will squash any perturbation that puts this data point off the data manifold. And the nice thing is, fast forward, let's say, 10, 12 years now, we are in the era of masked language models, and then all these masked language models are a specializations or the special instantiations of denoising autoencoders. And we know how to train these masked language models really, really well. And then all these big companies have trained the gigantic masked language models and have released them open source for our purpose. Although we're in the era of masked language models, the use cases of masked language models have largely been dominated by use them for initializing the downstream classifiers, which has been quite successful. But we're not going to do this. We're going to use it for another purpose, that is data augmentation. And why does it make sense? Now, one way to check whether these masked language models are in fact capturing data manifold is to really just use it by trying to start with a well-formed sentence, remove some of the words, and then ask this masked language model, BERT, to reconstruct or to fill in these missing words. If the filled in version corresponds to a well-formed sentence, then we would know that this BERT has learned to capture or characterize this data manifold very, very well. And in fact, Petroni et al. In 2019 showed that indeed BERT knows a lot about the word, and BERT knows a lot about what it means for a sentence to be well-formed. So let's look at one example here at the bottom. Sometimes virus causes infection. That was the original sentence. And they removed the infection and then masked it out and asked BERT to recover what the missing word should be. And according to BERT, disease, cancer, infection, plague, fever, all these are the highly probable words to come in the place of infection. And as you can see, all of them are semantically plausible. And also, all of them are syntactically plausible as well. So whatever the words we pick here and then plug it in, we end up getting a well-formed sentence. That is a sentence on the data manifold. And important thing is that we never actually designed BERT to do so. BERT just learned what this data manifold of natural language is. So we can now use BERT to sample from a local data manifold, starting from a point on the data manifold. And this is it. Well, the Simba, that stands for self-supervised manifold data augmentation, is a super straightforward and a simple algorithm. Now that we know BERT is sampling, or the BERT characterizes this local data manifold. So we start from the training set. We pick one training example, and we're going to corrupt it according to the BERT corruption function. And then once the corrupted version is fed into the BERT, we are going to ask BERT to fill in this masked out or the corrupted part of the sentence. And then that filled in version is going to be our perturbation of a training example. And that perturbed example is going to go into the original data set in order to dramatically increase the size of the training set. Now, the self-supervision comes from the fact that the self-supervision in the name comes from the fact that we can optionally use a already trained classifier in order to provide our labels for these newly added input examples. But as I said earlier, this is optional, and this is just one way for us to be able to impose some kind of smoothness on the target function. So we did some, extensive experimentation for text classification, in particular focusing on the sentiment analysis, and we also tested it on the natural language inference. We, in fact, ran experiments with machine translation as well, although I'm not going to talk about it in this talk, but you can check them out in the paper, which is on arXiv as well. And we compared it against the easy data augmentation, as well as the unsupervised data augmentation, both of which I already discussed earlier, and also conditional BERT contextual augmentation. I don't think this method is that sensible, just because if you know how to do the conditional generation, you can simply use the conditional generator to do a classification directly. So there's no reason to use conditional generator. So class conditional generator for data augmentation purpose. However, we tried to see if our method that is not class conditional can work as well as the class conditional BERT contextual augmentation. And then what we tested on 3 different types of the classifiers, because data augmentation algorithm should not be specific to the type of the classification classifiers that are going to be used after the data augmentation is done. So we wanted to see if that is also true. We tried recurrent neural net, well, LSTM, and convolutional network, as well as the Roberta that we fine-tuned. And what we see is that the use Simba to perform data augmentation almost always improves the generalization, both in domain and out of domain. And perhaps most importantly, Simba, the data augmentation by Simba never hurts the baseline accuracy, or it never goes below the baseline accuracy, where baseline refers to not using any kind of data augmentation. This is unfortunately not the case for many other data augmentation algorithms, because many of those data augmentation algorithms, such as easy data augmentation, those algorithms do end up generating all those examples that are off the data manifold, that are actively not relevant to solving the problem that we want to solve well. And then they often end up hurting the generalization accuracy. And then we could see that across all those different data sets that we have tried, as well as also on machine translation. Now, one interesting thing that we have found is that the number of augmented sentences per input training sentence, we saw that we didn't really need many examples or the many sentences that we need to sample from this BERT in order to get a good generalization accuracy. This one was interesting, but now that I think about it, looking back, it just probably tells us that the problem is too easy, or the data set that we considered was too easy. So if you're interested in more experiments and the results, please check out the paper. And I'm going to now move on to potentially a more interesting direction from here, or the more adventurous direction. So Simba is good. Simba is really nice. It never hurts the accuracy, but there's always a big question. Why do we have to do the augmentation locally? Can we in fact do the data augmentation that is not local to an individual data point, but is more global in a sense that if we look at the individual example in the context of all the other training examples? So we look at X, Y, as well as D. And this would, if we could, enable us to go much further away from any individual example, and it has a much better potential thereby for generalizing to far away domains. And both of these essentially are synonym to saying that it allows us to capture a larger portion of the entire data manifold. So what do we do? Instead of just looking at the current example XY and then draw some of the samples from the neighborhood according to P local, now we're going to look at both the current example and the entire data set to draw a sample X prime, Y prime such that it lies on the data manifold and is relatively close to XY, but still does take into account the entire data set. Of course, I'm definitely not the first one who asked about this question. Already in 2017, Zhang et al. From Facebook AI Research back then proposed the idea of mixup. And mixup is one of the most representative non-local data augmentation algorithms that has been proposed so far. And the idea or the underlying principle here is that a point on a path between 2 training examples lies on the data manifold. So if we could find the path between 2 training examples, both of which are already on the data manifold by definition and construction, any point that on the path that connects these two will also be on the manifold. So then what we need to do is we start from this XY pair. So our current example, we're going to sample another example from the entire training set that is not this particular current example. This is the part where we look into this training set. And then what we need to do is we need to find the path and then find the point that is interpolating between these two. And then the mixing ratio is going to be, again, also a random variable, a random number that we draw from some distribution between, that is defined between 0 and 1. And it turned out that we don't even need to have any sophisticated way to define this path between two examples. Simply a linear path between these two examples, so the line that connects these two, is enough, if and when it exists, of course. And in the input space, it just ends up being a linear interpolation or the convex combination of x and x tilde, these 2 points that we are considering, with the mixing coefficient lambda that was sampled from some uniform, for instance, uniform distribution over 0 and 1, between 0 and 1. And also you can do the same thing in the target space as well by considering the class label as a one-hot vector with one-hot vectors. How does it work? Because it turned out that as long as the collection of all these linear segments of all possible combinations of the inputs or the all possible pairs of the input examples cover the data manifold, the true, let's say, paths that are going to ensure that the the point along the path is always on the data manifold, then that's fine, because we are going to make our classifier smooth over this superset of the data manifold, and then in that case, and thereby, making our classifier smooth over the data manifold. So it's perfectly fine, and then it has been shown to work very, very well. But of course, what was the issue? What is the issue here is that there has to be a linear interpolation defined in the input space. But what if that's not the case? And indeed, if you think about natural language, there is no such thing as a linear interpolation between two sentences of potentially two different lengths. So recently, together with the Yekyung and Seohyung, who are research scientists at Hyundai Motors, yes, Hyundai Motors also has a research lab that works on the natural language processing, we decided to look at whether we can learn to interpolate for the purpose of non-local data augmentation in natural language processing. Now, interesting thing here is that if we want to say learn to interpolate, then we need to even define what it means to interpolate, because we don't, if we're learning to interpolate in a space where the interpolation doesn't exist, so we have to define what it means for us to interpolate between 2 points in a space where the interpolation is not really well defined. So to do so, we have to think about the generative learning suddenly. Now, what is generative learning or the generative modeling? We have a generative model M, and we are going to train it on a data set that consists of the unlabeled or the examples without any kind of annotation, and all these examples were drawn from this underlying data distribution P data. Now, once training is done, however we trained it, we can draw a sample from a model M, the generative model X prime. Now, in this kind of generative learning scenario, what does it mean for our model M to generalize? Generalization in generative learning, in fact, implies first that this X prime that was drawn from this generative model is unlikely to be one of the training examples. If all the samples that I draw from this generative model M were exactly identical to some of the training examples, we would call it overfitting. So whatever we draw from this generative model M cannot be exactly one of the training examples. Second, X prime, the sample, has to be still very probable under the unknown data distribution P data. What this means is that the X prime has to look realistic, and in other words, X prime has to be on the data manifold. And what this actually tells us, what these two criteria or the implications tell us, is that the X prime has to be some kind of interpolated version of X1, X2, all the way to Xn. Those were the training examples. So we have all these training examples, red colored, let's say, axis on the screen. And then all these purple axes are the samples that we draw from this generative model. And then they are kind of points that interpolate among all those different, let's say, training examples. In other words, generative learning, so the learning algorithm A itself, is a function that maps a set of points, x1 to xn, to a distribution that we can now refer to as interpolation distribution. If we draw sample from this distribution, that point is going to be or can be considered as a interpolated version of all these training examples. Now, what can we do then? We can now imagine building this learning algorithm A that's going to take as input not n many training examples, but just 2 training examples or 2 points in the space. And then it takes as input extra parameter lambda that is a mixing coefficient. Then it's going to output a distribution, interpolation distribution, given this x1, x2, and lambda. This actually becomes very obvious what the next step should be. We do meta learning. We're going to meta learn this generative learning algorithm A from a large amount of unlabeled data. And then that's going to give us a interpolation machine in this that can work, that can interpolate between any 2 points in the space where the natural definition of interpolation doesn't exist. How do we actually train it? So what should be the objective function for training this or meta learning this generative algorithm A? It turned out that the objective should just simply be a maximum likelihood. If I have the training examples x1 and x2 with the mixing coefficients lambda, we can imagine it as having an infinitely large training set. But in this infinitely large training set, the lambda portion of the set is simply the repeated copies of x1, and then 1 minus lambda portion, the rest of it is going to be repeated copies of x2. Then I can now write the maximum likelihood criterion as the sum of the log probability of either x1 or x2, given x1 and x2 and lambda. And then the weighting is going to be such that we have the lambda amount of the x1s and then 1 minus lambda amount of the x2. And by training this model or by maximizing this objective function, we should now get, or we should be able to train this algorithm A to give us the interpolation distribution. And what do? We simply maximize this objective function or the expected objective function, where the expectation is computed over all possible pairs of the inputs from the large set of unlabeled examples. And also we are computing the expectation over some distribution over this lambda, the mixing coefficients, which we can define it using some kind of beta distribution. And this looks pretty daunting, and thereby we use stochastic approximation, which is exactly what we do every time we train any kind of deep neural networks these days. So let's just look at how we implement it by looking at the parameterization. Now we know the objective function. Now we need to build in this learning algorithm A in the middle. We start with the very well pre-trained BART model, which is the encoder-decoder model. And then the encoder of the BART is going to encode the x1 and x2 individually into h1 and h2. And then these hidden vectors, hidden representations are not going to be just 2 vectors, but 2 sets of vectors. And these sets cardinalities correspond to the length of the inputs. And we use the technique that we developed for the non-autoregressive machine translation from last year. And we use the length, we convert the length, or up or down scale, the length of the size of these sets. And then the target size of these sets is going to be simply the convex combination of the length of the first sentence x1 and the second sentence x2. And once we have now projected everything to the 2 sets of the same cardinality, for each pair of the corresponding vectors, we compute the actual linear interpolation. So you can imagine that what we do is trying to lift the 2 data points that live in the input space where the linear interpolation is not really defined, we lift them into a space where the linear interpolation is now well defined and perform linear interpolation. Once the linear interpolation is done, we use the decoder of the BART to decode out either x1 or x2. Now in the training time, in order to compute this objective, we are going to decode out both x1 and x2 and then combine their log probabilities. Unfortunately, simply maximizing this objective function with such a parameterization is going to inevitably lead to the degeneracy. And then the major degeneracy is that there is no interpolation. What does that mean? Is that the probability mass, the entire probability mass of 1 is going to be simply distributed between x1 and x2, these two examples, and nothing else. And that's not going to be interpolation distribution. It's simply going to be choosing either of x1 or x2. So this is not good. So we have to introduce multiple regularization methods in order to avoid this no interpolation degeneracy. And then we use three different and then we use them at various places in our algorithm A. So the first one is the random masking. We're going to randomly mask some of the words in both the x1 and x2. And then this encourages the model to be able to use the contextual information in order to replace some of the words with the synonyms. Otherwise, these models will simply just copy over the exactly same words that appear in either of the x1 and x2, which is not desirable either. And the second one is we add the Gaussian noise in order to ensure that the small perturbation in this hidden space is not going to lead to a catastrophic or some examples that do not look at all like either x1 and x2. And finally, we add the decay towards 0. So we try to ensure that the L2 norm of these hidden vectors are not going to grow too much. And this has the effect of essentially packing the space with all these hidden vectors, ensuring that the linear interpolation between any points in this space will also be a reasonably looking sentences. So we use all three of them. In fact, these three of them are not out of, let's say, some empirical, let's say, observations or the empirical insights, but they are mathematical necessity in order to avoid weird degeneracies such as known interpolation degeneracy. Now, here comes a big question that I'm still struggling to answer. And then I do have the answer, but that is not the most satisfying answer yet. Is that is this interpolation distribution outputted by our model a meaningful interpolation? And what does it even mean for interpolation to be meaningful? So my answer relies on the authority of OpenAI and all these other big, let's say, players who have been training all these large-scale language models. If you have seen some of the examples coming out of, let's say, OpenAI's, let's say, GPT-3, or more recently, Google's, let's say, path-aware language model, as well as the few other ones from Facebook, as well as DeepMind, and were surprised or were impressed by what you get out of these models, then you have to believe me. You have to be on the side that these large-scale language models that we build, which includes what I just showed you earlier, does amazing interpolation. And the interpolation done by these generative models is meaningful. So this learning to interpolate is going to interpolate between these 2 points in a meaningful way. And how we know it is because we know that the generative language modeling on a large amount of data always gives us an ability to draw a sample of a text that looks very, very meaningful. So I'm going to rely on the authority and the cherry picking to answer this question. But for now, trust me, that is actually quite meaningful. So we call this algorithm Linda, so learning to interpolate for data augmentation. And then we have done quite extensive, let's say, analysis of this approach. So learning to interpolate. Of course, this is fully unsupervised. There's no labels being used, meaning that the analysis itself is difficult. But we've done some extensive analysis, and let me show you some of the examples, because these examples actually do shed light on a number of the important properties. So we're going to look at some of the extreme interpolation where the interpolation coefficient is close to 0.5. These are two reasonably good-looking examples of interpolation. So the Linda was trained on Wikipedia, and then we are testing it using movie reviews here. And then what you see is that the given two inputs the Linda is going to produce a third or the interpolated sentence that actually does mix in various parts of the two sentences that were provided. And then still whatever the Linda produces is very well formed, meaning that indeed Linda finds a sentence that still that stays on the data manifold and is in between these two input sentences that were given. Furthermore, what Linda finds is that the interpolation can be done at various levels. When we think about interpolating two sentences or the interpolating between two sentences, we think about interpolation at the semantic level only. However, that's not really true. The first two examples you saw were mixing a lot at the lexical level. Now, on the other hand, this example you see is that it's a mix of semantics and syntactic features. When you read them more carefully, what you see is that the content of the interpolated sentence is largely the content of the first sentence. However, the way in which it is written down is very much similar to the second sentence was written down, using a lot of dots. So we're mixing in the semantics from the first sentence and the syntactic features from the second sentence. And then because it's unsupervised learning, this is one of the things that just Linda figured out by looking at a lot of unlabeled examples. Now, unfortunately, Linda, just like any other neural language generators, suffers from the issue of hallucination. And we saw that this actually this happens quite often when the original sentences are out of the training domain or are off the data manifold that is not well formed. So this is one particular example. So Linda does in fact use some of the contents from the both sentences, but it tries to ensure that whatever it outputs is a well-formed sentence that is on the data manifold. And in doing so, it hallucinated some of the content that was not in either of the inputs. But for the purpose of data augmentation, which is where the idea is to make sure that our classifier is smooth over the data manifold, this kind of small errors shouldn't matter too much. And indeed, our experiments show again that the Linda is quite useful and then helpful in getting a better generalization accuracy, in particular when we work with a very low resource. That is that if we have a very small number of labeled examples. And then we were able to see again, just like what we did with Simba, that the Linda almost never hurts because what it generates as a perturbed example almost always stay on the data manifold. And then we could see that for across a number of data sets as well as the number of tasks. And then there are more experiments and results in the paper that is on arXiv at the moment. So this was a really fun, small step, but a fun step toward domain agnostic non-local data augmentation. And then one interesting insight we got was to view this generative learning as a way to induce the interpolation distribution and then mixing it together with the meta learning in order to learn to interpolate between 2 points that are in the space where the interpolation is not really well defined. So, yep, very fun project. Still a lot of ways to go. A lot of way to go, but it actually tells us that we can do such a domain agnostic non-local data augmentation for challenging domains such as natural language. Now, before I wrap up, I want to quickly touch upon this final piece of the work that we have done most recently, is to check whether this manifold assumption and its relationship to generalization actually holds in real life. So if you recall, what was the reason we wanted to do this vicinal risk minimization? It was because we expected that a smoother function, f, or a smoother classifier is going to generalize better along the data manifold. Now, is this really true? We somehow never asked. So we decided to ask this question by turning this vicinal risk into a smoothness measure. Now, given a classifier f, so we're not training classifier f, but f is given, and a target distribution, p target. Now, we are not even going to say that we're not saying that it's a training set, but this is actual test sets. So what are the test sets, or what are the test examples? Given these two things, we can turn the vicinal risk into a smoothness measure. How smooth is this classifier f on this target data point? That's what we want to check. And how we do it is that we're going to look at all those test set examples. And then for each one of them, we're going to look at the vicinity and then see in this vicinity how smooth this classifier's decision is. And we look at the average smoothness over all those different points in this test set. Now, that picture was not that great, so this is the actual reasonable figures to look into. So what we measure is that for each of the test point, we're going to look at the neighborhood. Now, what is the neighborhood? It is a local manifold. So neighborhood on the data manifold. And then within this neighborhood, we try to see whether this classifier F behaves smoothly or not smoothly. And then this is going to tell us about the smoothness of this classifier on that particular point. And then now, if we look at the average or some kind of aggregate statistics of this smoothness over multiple points, then we can now talk about the smoothness of this classifier on the target set or the target distribution. Now, I'm not going to go into details here because I'm running out of time already. But then using this, we can compute the smoothness of many classifiers on a target domain and then trying to sort these classifiers according to their smoothness, assuming all those classifiers were trained on a training set as well as it can. Because what is the most smooth or the maximum classifier of the maximal smoothness is a constant function, and then that's not the classifier that we are interested in. So we can now sort all these well-trained classifiers according to their smoothness, and then we can say that we want to check whether the sorted list corresponds to the sorted list of these classifiers according to their generalization accuracies. So what we did was to train a bunch of, as in like about 2,000 classifiers as well as we can while varying some of the hyperparameters. And then we really literally checked whether this sorted list according to a list of the classifiers according to smoothness metric and according to generalization correlate with each other. In order to test this, we tested, in fact, many different ways to capture or to characterize the data manifold. So just like what we talked about earlier, we can use the mask language model, or we can use the easy data augmentation, we can use the round trip translation, or we can just try to randomly replace some of the tokens. And then we compare our approach of using the smoothness metric against recently proposed the idea of average threshold confidence in order to check the generalization accuracy or the capability of a classifier on the out-of-domain examples. It turned out, surprisingly, to our surprise, I mean, we anticipated a bit, but not to this degree, is that the correlation, so the rank correlation between the sorted list according to the smoothness metric that doesn't use any label information, so we don't need any label information, and the sorted list of the classifiers according to their generalization accuracies, so which actually do rely on labels, is extremely high. In the case of the Roberta model that was fine-tuned, we saw that this rank correlation is above 0.9. So we could effectively sort these classifiers according to how well they were going to generalize without knowing the labels of the target set, which was pretty nice. And it worked for many different cases. One of the examples that we have in our paper is what we call extreme out-of-domain generalization, where we train these models on the movie reviews from Amazon as well as the other, let's say, domains, and then try to use it for the drug reviews from drugs.com. There's absolutely no overlap in products, and how the reviews are written also differs. However, what we see is that even then, using our smoothness metric, we can largely recover the ranking of these classifiers according to their generalization accuracies without using the labels. There are more experiments and results are in the table, but this is quite interesting in the sense that not because it has any kind of, let's say, practical consequences. I mean, we can use it in practice as well, but because it actually tells us that our basic assumption at the very beginning, that is that we want our classifier to smooth over the data manifold because such a classifier is going to generalize better, has been confirmed. because this entire research program of the data augmentation, not only mine, but the general data augmentation, hinges on this one particular premise. And then we haven't really checked it except for just indirect metric of whether when we use a data augmentation that actually relies on this particular premise, does it actually work, right? Hypothesis, does it actually work? But now, we actually check this directly, and then it actually tells us that indeed, we want to use data augmentation over the data manifold in order to make our classifier to be smoother so that it's going to generalize better. So it's confirmed. So, we can continue to work on data augmentation as a community. And we did some more analysis, and none of these analysis revealed anything too surprising or too, let's say, negative. So it's all good so far. So, and one last thing about this particular work is that it really reoriented how I view generalization, because as a machine learning scientist, I've been thinking of the generalization almost entirely from the perspective of, does this classifier generalize well? But it looks like that's the wrong question to ask. We should always ask whether this classifier will generalize well on a particular target distribution. So we cannot really say whether this model is going to generalize well without specifying to what kind of distribution or what kind of, let's say, subspace this should generalize. And here in this work, we actually see that yes, if we specify a particular target set, we do see that the generalization can be largely predicted from the smoothness of these classifiers, assuming that these classifiers were trained pretty well. However, all this work I have presented the 3 papers from my group during the past, let's say, 2-3 years on the topic of the data augmentation. Unfortunately, there are so many more questions left unanswered, and I'm going to just point out 3 questions that I'm very perplexed by at the moment and want to answer. The first one is that how general are the observations and conclusions that were made in this talk? Do they actually go beyond natural language processing? Now, I do have some evidence that a lot of these observations do apply to, for instance, computer vision, as well as biological sequence modeling. However, much more work needs to be done there. The second question is, as you have seen, almost entirely, all the things that have been done in my work in the recent few years have entirely been unsupervised, meaning that the data augmentation algorithms that I were able to come up with do not use any label information. And in fact, that's the only way. If you had all those labels, we wouldn't actually do the data augmentation. But then the question is, how does it actually connect to the unsupervised learning or the self-supervised learning's effectiveness as a parameter initializer? These two have to be, and they must be connected with each other, but what is the formal way in which we can write down this connection more explicitly? That's still a big question. The final question is, can we actually now then use these data augmentation algorithms, because they are all learned and they are largely agnostic to the domain, to make active learning finally useful and usable for more realistic problems? Now, this one is not a question, but more like, what can we do further? And then I believe there are many interesting directions that we can follow with this. With these 3 questions on the screen, I'm going to finish my talk, and thanks for the invitation, and thanks for listening all the way.
Fantastic, Kyunghyun. Very, very inspiring work. Thank you very much for that. I learned a lot today. We have quite a few questions in the chat. Okay. Let me try to pose them. The first question is from Sergio Ferro. He writes, I understand that all the new samples for any vicinity are mapped to the same label, and then the model is trained on the whole augmented data set. How is this different from making a model with the original data and then assuming that any perturbation to data close to each X will be classified with the same label? Does a manifold act as a modeler for X, for the neighborhood of X?
Yep, the answer is yes. That's the answer. So precisely this, all these unsupervised learners are characterizing this local manifold structure, and then that actually allows us to use it in order to impose or encourage the classifier to act smoothly over the local data manifold. So the answer is yes.
Great, thank you. Let's go over to the second question from Akari Berada. How to do data augmentation with specialists in domains like finance or law or pharma with transformer models?
Mm-hmm. Yeah, so this is a good question. I mean, I'm not too familiar with the finance nor law, a legal domain, but I am actually spending half of the time in one of the largest pharmas in the world. So I do look at a lot of the different problems there where the deep learning has been used. And yes, data augmentation is in fact very, very important in this kind of pharmaceutical, the drug discovery domain, just because the amount of the discrepancy between the amount of unlabeled examples and the amount of the labeled examples is quite extreme. What that means is that we actually have to use data augmentation that is based on learning based on unsupervised learning because we have a lot of unlabeled examples. Now, has it been successful? We're trying, but hopefully in next time I come talk here in Vienna, I'll be able to report some positive findings. Yes.
Great. We're waiting for that. Then we have a question from Pedro Jeruzo from RI. So very insightful talk. Thank you so much. It is very interesting that you need to impose to Linda different techniques to avoid just copying X1 or X2. Do you know what underlying properties these techniques have that allow to interpolate between these two? I would like that the intuition built before adding the techniques work alone, but they don't. Why?
Right. So essentially this no interpolation degeneracy is essentially equivalent to overfitting in generative model. So two things that I talked about, or the two implications from generalization in generative learning are that the samples that we draw from these generative models do look very similar to training examples, but cannot be exactly training examples. And then if you think about this no interpolation degeneracy, that's where essentially this generative model learns to output only the training examples that are X1 and X2. So, a lot of the techniques or the ideas that we have developed in order to ensure that generative models generalize can be used for Linda. In fact, some of those regularization techniques that we use are indeed some things like this. So for instance, random masking in the input is the idea we got out of this masked language model, which is one of the most widely used unsupervised learner these days. And then adding Gaussian noise and then trying to encourage the norm of the hidden states to be close to 1 or 0. Those techniques actually do come from the variation autoencoders where we have the KL divergence from the posterior to the very simple prior. So in a sense, yes, all the things that we have learned and all the things that we are going to learn from unsupervised learning will be applicable and should be studied.
Thank you. The second question by Akari Berada. Can we combine data augmentation with transfer learning?
Yes, indeed. So in our work on the Simba, the first work that I presented, let me just go there. So of course, it depends on what we mean by transfer learning, because transfer learning turned out to be extremely overloaded these days. But if by transfer learning, we pre-train a, let's say, masked language model and then fine-tuning it on a target, let's say, downstream task, then the answer is yes. In fact, one of the classifiers that we tested, the Roberta, was already pre-trained on a large amount of unlabeled examples. And even there, we saw that the Simba or this kind of data augmentation was beneficial simply because fine-tuning may actually break this smoothness imposed by the pre-training. However, creating all these augmented examples ensure that even during fine-tuning, the smoothness is maintained. So the answer is yes.
Great. Seth Stafford asks, which paper does a risk a smoothness measure analysis?
Yes, I just realized that the paper may not be on arXiv yet. I'll just send the manuscript to the organizer so that they can actually just distribute it within the institute after the talk. Yes.
Sounds good. We'll put it on the side. Alexandra Kruger asks, says, thank you very much for the great talk. Did anyone try to interpolate over more than 2 data points, sentences for language models?
Yeah, thanks for the great question. In fact, we haven't tried it yet. We only use the two sentences. However, if you look at how the Linda was created, in fact, there is no reason why it has to be only 2. It could very well be any n many sentences as the input. This is a great point. Now, will there be any challenges? I don't know. I think this is definitely worth trying. Yes. We just haven't got to it. Yes.
Great. Negara Ninagi asks, says, thanks for the interesting talk. I'm not an expert in NLP or data augmentation, but I have a more general question regarding data augmentation using the generative technique. As far as I understood, the data manifold is a broader space of the realistic looking data. Would it be possible to subsample parts of the input data and create a new sample which is still on the data manifold, even though it's not completely realistic? Imagine I have a data set of human face drawings, and somehow I can manage to take the eyes, nose, lips, and so on from different images and create a new sample and still use it as a sample of the manifold. It might not be as realistic or a realistic face, but it still is a human face.
Yep. So the answer is again yes, in a sense that, and then this was answered by essentially the mix-up paper. So in mix-up, most of the points that we get from a linear interpolation between any two training examples is not going to be on the data manifold. However, if you look at the collection of all those linear segments coming out of the all possible pairs of the training examples, that collection is going to cover a large portion of the data manifold. And thereby, if we make the model smoother over this larger, let's say, superset of the data manifold, the classifier is going to be smooth over the data manifold and is going to work well. And then this kind of something that looks like a face, but that does not look too realistic, still is fine, as long as in this many combination of these different, let's say, face parts, some of them are going to look like the face. So as long as you make the classifier to work smooth over all possible ways in which the face parts can be combined, there will be some combinations. They're going to look realistic, and then that's going to make this classifier work smoother on the realistic faces as well, and then thereby getting a better generalization. So the answer is yes.
Great. I have two more questions from the audience. Valentina Shastivania, I'm hoping I'm right, pronouncing it correct. Thank you very much for sharing your results. I'm really interested in Linda. If Linda may be applied to DNA protein sequences. You have mentioned this domain. Do you have plans to investigate Linda's performance for drug discovery?
Yeah, so I want to. Yes, that's definitely true. So our team within Genentech, Precision Design, we have a lot of things we want to try, but the team is still growing, and then not at the level where we can pursue everything. So definitely possible, because I don't know if you have noticed, although all the experiments were done on natural language domain, but the algorithms were all constructed to be quite generic. So as long as the input is a sequence of some discrete symbols, all these algorithms are directly applicable. And indeed, many of the masked language models have been used for modeling protein sequences as well as the DNA sequences in recent years. And there is absolutely no reason why I cannot see any reason why these data augmentation techniques based on this unsupervised learning could not be applied to these domains in biology as well.
Thank you. And we have also the last question from David Cradle from ARI. What are your observations in terms of increased or reduced model bias as a function of more or less augmentation?
Yeah, so I mean, depends on what kind of, let's say, which sense of the bias this refers to. But generally, if we add any kind of data augmentation, then we are introducing bias and thereby minimizing the variance. Now, which direction does that bias actually move the classifier toward is a big question. I don't think we know how to characterize it really well. However, what we have seen is that at the end of the day, if our goal is generalization and the robustness, we want lower variance over lower bias. So that'll be my kind of statistical learning theory head answer. And if the bias is more about kind of, let's say, the encoding of the social biases into these classifiers, now using these large-scale pre-trained language models or the unsupervised learners will indeed produce the examples that are going to let's say reflect the kind of social biases definitely. And then maybe some of these classifiers are going to work better or generalize better by being more smooth over some of the domains that are more prevalent in the society at the moment, and that might actually does result in the discrepancy in the subpopulation accuracies, and that could be undesirable, but we haven't really looked at it yet ourselves.
Thank you very much. We have 1 more minute, so I would like to ask one more question, if it's okay for you. You talked about the meaningfulness of the interpolation, right? So have you considered any empirical approaches to evaluate this?
Yeah, so that's a really good question. I mean, the only thing that we have is our kind of manual inspection of some of these examples, and then we could think of running some kind of human evaluation in order to check the quality. However, we haven't really looked at it that carefully yet, because at the end of the day, the notion of meaningfulness is probably very subjective, and also it does not correlate directly with the downstream accuracy on the task that we are actually solving. So we're still thinking at the moment about what is the right way to even define it and measure it.
Thank you very much. Kyunghyun, thank you for the very interesting and informative talk. Thanks everyone.
Great fun, yes.
Thanks everyone for listening. Kyunghyun, thank you very much. And everyone,
thank you.
Have a nice evening. Take care. Hope to see you soon. Bye-bye.